Good morning, everyone. Welcome to another LIP seminar. And today we have the absolute pleasure to have a founder member of the Atlas collaboration, Professor Philip Allport from the University of Birmingham, and director also of the Instrumentation Laboratory for Particle Physics and Applications. So Professor Philip is an expert in developing radiation-hard technologies for particle physics experiments and led the development of prototyping and several instruments for the Atlas detectors. So he's also a leading proponent of the high luminosity LHC program. In addition to his impressive career, he currently acts as the chair of the ECFA detector panel and the R&D roadmap panel as well. He also played a role in setting the agenda for future detector developments, and that's exactly the topic of today's seminar. And we are very much looking forward to hear your seminar about Detector R&D in support of the European strategy for particle physics. So thank you very much again for agreeing to give a seminar at LIP.
Well, thank you very much for the invitation. And of course, I'm only sorry not to have had the opportunity to be there in person, but hopefully that will come at another time. So what I thought might be useful to cover are two related topic areas. So first, I will take you through some of the recommendations from the very recently completed and published ECFA Detector R&D roadmap. And so there's the CDS link where you can find the documents. And what I'll talk about is some of the motivation, the process, our key observations and recommendations. And it's just a montage of some of the different technology areas and experiments, future facilities that we've been considering. And then very much in the same context, but changing tack a little bit, I'll talk more about FCC specific R&D, so things which are more based on European future collider planning. And so I'll say something about the experiment concepts, then I'll go through the different topics and their requirements for vertexing, tracking, calorimetry, particle ID, photodetectors, microelectronics, and then the muon systems, magnets, and integration, and obviously finish with some conclusions and observations. So this process started really with the update to the European particle physics strategy, which was adopted by CERN Council in 2020. And in the main report, there is a discussion on Detector R&D, and it's one of the messages is that coordination of R&D is critical. Some areas of coordination already discussed in the document, such as AIDA, TRACT, EP department, and the RD collaborations, but really to maximize the scientific outcomes, they want to make the most efficient use of resources. And so there's a clear need to strengthen R&D, existing R&D collaborative structures and create new ones to address future experiment challenges in the field beyond the high Lumi LHC. So the focus is beyond the high Lumi LHC, and organized by ECFA, a roadmap should be developed by the community to balance the detector R&D efforts in Europe, also taking account of adjacent fields. And then in the longer deliberation document, there is another discussion of R&D programs and infrastructure in national institutes, labs, and universities, and synergies with other fields and industry. And there again, the instruction is collaborative platforms and consortia must be adequately supported to provide coherence in the R&D activities. And again, the community should define a global detector R&D roadmap that should be used in support of proposals at European and national level. So that's really what set the framework for this. Clearly, the role of ECFA is central as the organization of this. And there are a number of presentations through the process to ECFA listed there, culminating in the plenary ECFA presentation where the final report was approved. And many more details on the roadmap process can be found at the link at the bottom. So this is the organizational structure that ECFA set up. You see that we divided the topics into what you might call broadly 6 technology areas, and then 3 transversal areas of electronics and on detector processing, integration and training. The makeup of the panel is shown there. The panel consists of the coordinators listed in black, with again interaction with ECFA and the laboratory directors group representative who were charged with setting up a parallel process for accelerators. And also listed there are the 2 conveners of each of the task forces who are also members of the panel. And it was primarily through the task forces that we organized the interaction with the community. So what you see here is that the interaction with the community happens through the task forces, but also through restricted ECFA, which has representatives from each of the ECFA participating countries, and they played a key role in also helping to provide community inputs at a national level into this process. Similarly, within ECFA, there are representation of the most closely neighboring fields of represented by NUPEC and APEC for nuclear and astroparticle physics. And through those contacts and also through the individual task forces, again, they were charged with communicating with neighboring disciplines to basically explore synergies for technologies in particle physics with the other areas. So what we identified were the areas in the European strategy update which were listed as high priority future initiatives and other essential activities for particle physics. And so what we aimed to do was to start from the Future Science Programme and to identify the main detector technology challenges to be met. And within each task force, we were looking to prepare time-ordered R&D program in terms of capabilities which are not currently achievable. So I'll only go through these very quickly, but the topics which are listed in the strategy update are the full exploitation of the HLLHC, R&D for long baseline neutrino, technologies needed for detectors at future Higgs electroweak top factories in all possible manifestations, i.e. linear and circular, and with energies possibly considered up to the TeV range, and then a long-term R&D vision for 100 TeV Hadron Collider with very high luminosities and beam crossing rates, beam crossing rates similar to the LHC. Then a program to also explore the possibility of detectors for muon colliders, and then those accelerator developments, accelerator-based rare decay processes, dark matter exploration and high precision measurements, R&D for optimal exploitation of experiments studying partonic structure, so this would be interfacing with NUPEC science areas, and then the very broad range of R&D areas in non-accelerator including dark matter searches, reactor neutrino experiments, and also neutrino observatories and other interface areas with astroparticle physics. So so it's not our job to say which of these science areas is the priority. It's our job to say what detector technologies should be prioritized to make sure that these science areas would not be delayed by the availability of the detector systems required. And so in addition, we looked at the facilities for detector evaluation. So outside the experimental program, what's needed for detector R&D in terms of test beams, irradiation, technological workshops and laboratories, networking structures, etc. And you'll see the recommendations have a lot to say about organizational aspects, and also, as discussed before, overlaps with neighboring fields and opportunities for industrial partnership. So the process that we went through, starting in 2020, we worked through largely putting the task force structure in place in 2020. Then 2021, the first half of the year was very much put into the expert and, expert and community consultation process. So we started with presentations by leading representatives of the future facility areas, very much along the lines I just outlined in black in the previous two slides. Then the task forces launched questionnaires, which went to the respective national communities through national contacts appointed by restricted ECFA. And the task forces liaised directly with experts in the ECFA countries and in adjacent disciplines and industry. And these then fed into a major process of day-long open symposia, which were widely advertised and very broadly supported in each task force area, that then provided the inputs which were collated by the panel. And then we took this into a 4-day drafting session, which allowed us to make our main recommendations, which were formally presented at the ECFA EPS session to the particle physics community. So the main recommendations are unchanged from those shown in the slides there. We have iterated with restricted ECFA before presenting these recommendations. We have taken further feedback from the community, and the full documents were then prepared towards the end of last year and presented for approval to ECFA in November and just before Christmas to CERN Council. And again, many more details can be found in the link shown there. So I'd like to pay tribute to the very large number of people who've helped in preparing these documents. We have listed first the input sessions and the presenters, who I hope you'll agree are really leading representatives of the different areas. So we had 12 expert input session speakers. We had the ECFA national contacts who are listed there. We had, through the 9 task force symposia presentations, we had 121 presentations. The task forces also launched surveys which were distributed by the national contacts, and the attendance at the symposia, we had a common sign up with just under 1,400 people participating, and also in the adjacent fields, linking to each of the task forces, we have another 44 experts who've been appointed by the advisory panel with other disciplines, and those appointees have come from APEC, ESA, LEAPS, LENS, and NUPEC. And you see listed there all the authors of the report, not just the conveners, but all the expert members of all the individual task forces. So this has been really quite a large process driven by a large number of people. And the outcome summarized in a 250-page main document and an 8-page sort of more glossy synopsis for less specialist reader, or maybe the less attentive reader, thinking perhaps of representatives at CERN Council who may not have the patience for reading all the technical details in the longer document, but the 8-page synopsis also summarizes the key recommendations from the main document. And a guiding principle throughout this has been that we are not setting the priorities for what should be the future facilities, but we are trying to ensure that whatever direction particle physics takes beyond the high luminosity LHC, particularly in Europe, that detector R&D readiness shouldn't be the limiting factor in terms of what defines which futures for particle physics are practical. So our role is, the role we adopted was very much to identify what has to be done to make detector R&D readiness not a time limiting factor. So based on that, we collected in collaboration with ECFA and the laboratory detectors group, a list of facilities, which I'll show in a moment, for which we attach the time when we regard the earliest practical time that R&D would need to be completed for those facilities. And then we turned this into a list from which we derived for what we see as the key detector research and development themes in each of the 6 task force areas for technology, and then again in electronics integration and training. We turned this into the timeline that we saw as necessary, and the timeline recognizes that for each of these different developments, there are stages along the way when the R&D is required, but often this is R&D on a smaller scale or less stringent specifications, leading through to the final facility for which a date is known at the moment, when that technology would be needed. So, for example, in the first few faded arrows represent the timescale when FCCE may be required, and the faded region represents the time between the R&D for that needing to be completed and the earliest likely realizable start date for FCCE. And similarly, the longer arrows going beyond 2045 for technologies which lead to things which are specifically needed for FCCHH. And then in other task force areas, like in the liquid detectors, or particularly particle ID or quantum technologies, you see a number of arrows ending on sooner timescales, and this is not indicating that R&D is not anticipated beyond these points, but these are the furthest into the future that we have firm dates for facilities for which these R&D topics, the R&D theme areas, would be required. So I won't go through all of these now in detail. I would invite you to look at the document, but I will say a little bit more about these as I go through the individual task force areas. So you can find more at the plenary ECFA presentation, and I've really, for these slides, just copied what was shown in the presentation there. As I said already, the dates used have a deliberately low precision and correspond to a kind of earliest feasible start date after consultation not only with the facility proponents, but with the laboratory directors group who are preparing the corresponding accelerator R&D roadmap. Obviously, the two have to be aligned. And we've limited ourselves to those projects which are actually mentioned in the European Particle Physics Strategy Update. Although, there are other possibilities which we think are effectively covered by the things we already mentioned. So, the various various facilities in the different time bins are shown both for accelerators and non-accelerators, and even in the case of non-accelerators, should emphasize that this is only a sample of things. And then within each task force, taking these list of facilities and the timing in those diagrams, the task force has taken those key themes I discussed and seen for each of them what is the time scale which looks most critical. And so the dots shown here try to illustrate not so much the difficulty associated with the R&D, but the extent to which that particular topic is critical to that particular facility, i.e. if the R&D is not met in that particular area, whether it's sufficiently mission critical that the actual facility would not be realizable with the physics goals that it has. So these dots really say what must happen, or the physics goals cannot be met, what's important for the physics goals to be met, what's highly desirable to enhance the physics capabilities, and what's basically already in process. So trying to identify how urgent the R&D is, driven by the different science areas. And so we've done that in all the different task force areas which are technology based, including the transversal task forces for electronics and integration. And as you can imagine, when things refer to, for example, the timescale of FCCE, features like radiation hardness become really paramount of importance. So I won't go into the details for the sake of time, but though just to give you a flavor of what sort of aspects are discussed in the document. And then in addition to these task force specific areas and task force specific recommendations based on the future facilities, there are some general strategic recommendations around Detector R&D. So clearly there needs to be better coordination for the availability and support for test beams, for large-scale generic prototyping and irradiation facilities. And whilst some of this has been provided in the past by organizations such as AIDA, they've still been limited in scope, and also in the latest version of AIDA, there isn't already that support for the infrastructure in terms of transnational facilities, which was there in AIDA 2020. Engineering support, we see that as detector concepts get more complicated and more integrated, more really professional engineering starts to be required, of the sort that does require some expertise and resources that maybe needs to be focused at some of the larger centers. Again, support for instrumentation specific software, things like GEONT, in the gaseous detector world, Garfield, making sure the community has access to TCAD and facilities like that. All of this needs to be organized at a European level. And then looking at the RD collaborations that exist, we would recommend a major refresh of the way in which all of this is organized in Europe, with encouragement for more R&D collaborations than the existing ones, RD 50, 51, 42, 53, etc., to be formulated. We see that in some areas, the sheer complexity, specialization, and cost means that individual smaller institutes will struggle to basically achieve a critical mass. And therefore we think a tiered structure in a way that looks a little bit like the tiered structure we use in grid computing would be promising, where you have some national centralization at larger institutes, but a more fluid way in which smaller institutes can participate, but still making sure that the critical mass of experts and expertise is achieved, and also available to basically interact with a sufficient large volume consortium with industry, because in some of these areas it becomes very difficult for smaller entities to really have sufficient weight to be able to interact with larger industrial centers or corporations. We believe that much of European R&D is organized in ways which are responsive grants, which are 2 or 3 years, and this doesn't allow strategic support with R&D investments lasting over decadal timescales. We also wanted to emphasize the importance of blue skies R&D and support for the more riskier activities, for which maybe a more responsive R&D funding mechanism remains very important. A vital area that was the focus of Task Force 9 is the really urgent issue around the way in which the people we rely on are nurtured within our community, the way their careers are structured, and to make sure that the field of detector R&D activities is sufficiently attractive that we can continue to make sure that the most talented people are attracted into our areas, and in particular, where you have key skill sets which are highly specialized, that we have appropriate retention, including adequate remuneration. Then we should build closer links with industry, which will also benefit from having longer term funding mechanisms. And it's absolutely vital that we move more towards open science, and specifically public funded research in the area of instrumentation development, particularly in particle physics, should be in open access publications. So that basically is the ECFA part of what I wanted to talk about. So that's the broader context. And now what I want to focus in on are the areas linked to the Future Circular Collider in Europe. And clearly the recommendations from the European strategy emphasize the vital importance, as I said, of a future Higgs electroweak top factory for the next steps in terms of the exploration of the universe in particle physics after the HL-LHC program. So, you know, equally important are a number of other topics in areas of non-accelerator physics, in other accelerator based disciplines, but probably the major future accelerator collider-based facility that we are looking to promote will be in this area. And the European model for what that should look like is embodied in the Future Circular Collider, which would be a two-stage program with first an E+E- machine in a 100-kilometer tunnel, which would then be available to install a Hadron Collider on a later timescale. So I will first start talking about FCCE, and here the idea is to have two, but increasingly the idea, the option of 4 is being explored: interaction regions. And the aim is to have a Higgs factory which would be able to produce over 1 million Higgs through Higgs-Strontium, E+E-, 75,000 through WW boson fusion, and would also achieve sensitivity, indirect sensitivity to the trilinear gauge, trilinear Higgs coupling, and would have high enough statistics to also be able to explore S-channel Higgs production in E+E-. The electroweak program involves a huge increase in statistics over that achieved at LEP in Z, W pair and top production, which would give indirect sensitivity to physics up to mass scales in the 70 TeV range. And in terms of flavor physics, it would actually be achieving rates of production which are competitive with what will be produced at dedicated factories, but of course with different kinematics, and therefore the ability to explore rare decays and production mechanisms in a very different regime, for example, to that going on in Japan. And there'll also be the possibility to look for feebly interacting particles. Sorry, that is my phone somewhere going off. Let me turn that off for now. So the specifications are really designed to control systematic errors at the 10⁻⁵ level, because with these huge statistics, the thing which would be limiting in terms of detector capabilities for the physics goals of FCCE would be if the huge statistical precision could not actually translate into the final physics precision achieved. So absolutely key is the precision capabilities of detectors for this environment. So in terms of tracking capabilities, in terms of electromagnetic resolution, jet energy, things like the systematic errors coming from the B field stability, the luminosity determination, which is a major topic in itself, with the aim to achieve a precision of order, 0.1 per mil precision on luminosity, and beam energy needs to be very well determined, and the beam energy spread needs to be measured very accurately, and that has particular requirements for very accurate tracking of dimuons in the forward region. And obviously for the heavy flavor program, you want to optimize secondary vertex measurement with a flight path resolution down to 0.2 microns for very accurate lifetime measurements. Particle identification through a number of technologies being pursued in the two different detector concepts, which are either a click-like detector, which silicon tracking, and scintillator ion HCAL, and a silicon tungsten electromagnetic calorimeter, or the alternative technology of the IDA, EA, Innovative Detector Electron Positron Accelerator detector, which is to have a very large scale gaseous detector, against, in both cases, CMOS sensors for the vertexing, and then calorimetry outside a coil with pre-shower counters just inside the coil. There's also an evolution of the LHCC proposal for an FCCE detector, which is complicated by the fact that running at a operating hadron collider, you have to find a way of steering 3 beams through your interaction region, the electron or positron beam, as well as the colliding hadrons. And this involves complicated magnetic structure and the detector, asymmetric detector layout, which emphasizes measuring the backscattered electron with very high precision to achieve the X range required. And there are some specifications for the Electron Hadron proposed detector. And then the most extreme requirements are for the Hadron experiment. This would be operating with pile up in the range of 1,000 events. Obviously, at 100 TeV, you have very high transverse momentum that you need to be able to track. So tracking with 10% resolution up to 10 TeV. The calorimeter, less extreme requirements than for E+, E-, for the ECAL, but still something that's quite difficult to meet with a lot of the technologies that can survive these radiation environments. Forward detector capabilities to an eta of 6. HCAL achieving at least the same energy resolution as is currently managed, for example, with the TILE-CAL of Atlas, and muon system again giving precision measurement up to 10 TeV and a very high central magnetic field and a very large magnetic volume. So this shows some of the layout concepts for this detector, the complex magnetic field and the extreme radiation field that will be encountered with up to 10 to the 18 fluences up to the 10 to the 18 neutron equivalent in the worst cases. So we have radiation targets which are a factor of 100 above what's currently achievable for the high LUMI LHC. And this is reminiscent of where we started in the early 1990s, when we really had no way of knowing how to build detectors which could cope with the radiation levels that were projected for the LHC in those days. And so this has been the focus of a number of instrumentation initiatives, as well as the requirements for other future facilities. The US Department of Energy Basic Research Needs Report, the SNO Mass Instrumentation Frontier Studies, AIDA, and the CERN EP R&D initiative with the topic areas shown there. And of course, these are key to the document itself, the roadmap document. So for the technologies, which is the final area I want to talk about, so for vertex detectors, the emphasis is really on taking CMOS pixel sensors to a new level, building on, in particular, the very nice studies done for ALICE 3, for ALICE upgrade, and for future ALICE 3, where the idea is to have very thin stitched detectors, wafer scale integration that can actually be curled around the beam pipe, giving remarkably small material and spatial resolution of order 3 microns. Of course, additionally for FCCHH, you have huge challenges in terms of vertex detector requirements for radiation damage, not just for the sensors, but also we have no way of knowing what microelectronics could survive in such an environment. Increasingly, you see fast timing combined with high spatial precision as a requirement, what's often called 4D tracking capabilities. And LHCb is already developing this for the next upgrade of the Velo in long shutdown 4, where they would like to combine a spatial resolution of 10 microns with 50 picosecond timing resolution. NA62 is also aiming for this. And in the longer term for FCCHH, one would like to be achieving a spatial resolution similar to LHCb, but over a larger area, and even better timing resolution, obviously with a much larger area detector than LHCb, and with a much higher radiation environment, even though for LHCb, the radiation will still be a significant challenge. And so we have timing detectors where we may use 3D structures, or we may use ultra-fast silicon detectors using low gain LGAD developments, where a lot of work is going on into improving the dead region of LGADs through reducing the gaps between pixels, AC coupling, or inverse where you read out from the other side. And the dream still remains incorporating all those features into a truly monolithic solution, just as the CMOS solutions are truly monolithic electronics and sensor combined in one detector. Tracking either gaseous detectors for FCCE in IDEA, the idea would be to actually use a highly transparent drift detector. A TPC is not so favored because, unlike a linear collider, you don't have the possibility of using gaps between electron bunch trains and gating. CLD has silicon based solutions, building on, again, on the CMOS sensor developments. And for FCCHH and EH, you would like, again, 4D tracking and radiation tolerance, which could be in the range which will be realizable in CMOS sensors rather than requiring the use, as in current HLLHC, of hybrid detectors, for example, strips and readout chips. Calorimetry, a lot of developments based on work that has been done for the linear collider by the CALIS collaboration, silicon, gaseous and crystal-based and scintillator-based readout schemes. And so the ideas which are being looked at in the different detectors illustrated here for E+, E-, they're building on the ideas of CALIS and including crystal, high precision crystal studies for EH. You have systems shown there, which would be largely based on scintillators, and for HH, liquid argon or liquid noble gas is considered for much of the detector, particularly the forward region, as being the only viable radiation hard technology. But the barrel ECAL, you may be able to use a silicon-based solution, maybe a CMOS-based solution, silicon tungsten, because the radiation hardness of silicon is probably adequate for the sort of 10 to the 16 neutron equivalent range that you would expect there. There's work going on different particle identification technologies, particularly trying to make these compact for future E+, E- detectors. There is a particular issue that as you go to more advanced technologies, the prototyping costs become higher and higher. And so it becomes particularly important, I think, to find ways of reorganizing what we do to have a higher concentration of effort, maybe in just a smaller number of groups that are able to achieve the critical mass of expertise and resources for dealing with these very high R&D costs. So that's a particular issue for microelectronics and microelectronics-based detectors like CMOS sensors. There's a lot of new developments in gaseous detectors, a real renaissance in terms of micro-pattern gas detectors. They're the most cost-effective route to instrumenting large areas. I've discussed the central tracking for E+, E-, but also the readout of TPCs using technologies using micro-pattern gas detectors, or combined gas and silicon detectors, where you might have pixelated sensors reading out the drift electrons from the ionization in a TPC. You're pushing temporal and spatial resolution. RPCs offer very good timing resolution. There's cooling technologies, ultra low mass stable supports, novel materials, and also all the issues around infrastructure for test beams, radiation hardness, etc. So my final point is that major R&D funding for the LHC Detector R&D program was actually in place as early as 1986. The timescales are very long, and the ECFA Detector R&D roadmap starts from looking at what we need to have in place for programs which have timescales which are really looking into the 2030s and 2040s. I can't emphasize enough that the R&D is urgent to start now for facilities, even if they're only targeting starting in the 2030s or 2040s. And we're trying to identify the mission critical R&D, where mission critical for something like FCCE can just mean trying to find technologies that will function adequately in this very challenging radiation environment. But in other areas, such as FCCE at the luminosity frontier, mission critical means that the high statistical precision is not compromised by systematic errors coming from detector performance issues. The FCCE program represents a very exciting but challenging future for future particle physics in Europe. But without the required investment in detector R&D, we will not realize the opportunities that this offers. And the lead times of at least 20 years should be anticipated for the more demanding technology aspects. And in some cases, it's not even clear what would be the best R&D directions to go, because the challenges really go beyond what any known technology can today support. So that's everything I had to cover, and I hope that's an interesting or useful overview.
Thank you very much for this very nice overview. So you were perfect on time, so we have plenty of time for questions. So yeah, please raise your hand, or if you have problems, you can just speak up. So Patricia, yes.
Hi, very nice presentation. I have a question. Okay, that you motivated with your conclusions. You said that there are areas that are so challenging that it's not clear the direction to be followed up in the R&D. Can you name some of those, for instance,
yes,
that will be really difficult to achieve?
Yeah, as I said, it's, for example, sensors or microelectronics for the FCCHH. I mean, for FCCHH, I think it's really difficult to see how the radiation environment, which is a factor of 100 worse than the vertex detectors at HL-LHC, will be met. There are, interestingly, on a shorter time scale, similar challenges in terms of the very forward detectors, even at FCCE. And given the absolute importance of having this very high precision luminosity measurement, so if you want to measure the luminosity at a E plus E minus circular machine with a precision of 1 part in 10 to the 4, you actually do need to have high granularity detectors very close to the forward, very close to the beam in the forward direction. And in terms of ionizing dose, the radiation levels that you have to withstand there are also things which are not currently easily achievable with any existing technology. So it's not just hadron colliders which can pose real problems. Also, you know, fixed target vertex detectors, you have challenges that need to be met, and experiments which have you know, very close detectors to the beam. As you know, LHCb, the inner rings of the velo mean that the radiation environment, as you turn up the luminosity that LHCb tries to accommodate, also get you into regimes which are very challenging.